important aspect of Newton's laws we'll discuss today. Constraint relations by something called virtual work or virtual power theorem. Okay. So this is a very powerful and generic kind of method for developing constraint relations, which will be very useful for us in solving problems not only in Newton's laws of motion, but also solving problems in general mechanics in future chapters also. So this is like a fundamental building block of that method. So this is something you need to pay attention to and understand very carefully. So we'll understand it in context of multiple pulley system first, okay, and then we will see how it can be applied in different situations also other than multiple pulley systems. So the general idea of this virtual work or virtual power theorem is that any internal force within a system. Okay. So what do we mean by this internal force within a system? So for example, okay, the tension in a thread within a system consisting of blocks and pulleys. Okay. Or another example is the normal contact force between bodies or blocks or whatever in a system of multiple blocks or bodies. So these type of forces we mean by internal forces. So when I'm talking about internal force within a system, I mean this type of force, either the tension in a system that consists of blocks and pulleys, or the normal contact force in a system that consists of multiple blocks, that kind of thing. Okay. So always such a force acts in such a way the net work done, okay, or we can also say net power developed by it in the system is zero. Okay. So just first write down the definition, absorb the statement. Then as I give numerical examples of this or physical examples of this, it will become clear what we mean by this. But this is a general way of expressing the theorem itself, that whenever within a system we have an internal force acting, like the tension in a thread or the normal reaction contact force between different blocks that are part of the same system, then this internal force will always act in such a way that the net work done by it will be zero within the system, or the net power developed by it within the system will be zero. So of course, I realize that we are not that much familiar with concept of work and power yet. So I'll give you the basic definition of work done and power also. Okay. But many of you will be aware about work done by a force as a definition from 910, and you will also realize that we had discussed about work done in terms of scalar product or dot product when we were discussing vectors. When we were discussing dot product of two vectors, we had seen that force and displacement, if we calculate their scalar product or dot product, that gives us the important scalar quantity of work done. So we'll of course take a relook at that before we understand how to apply this theorem. Also, before we get into the theorem, like I said, let's first take a relook at what is work done by a force. Okay, finish writing this down. So before we get into the application of the theorem, let's once again understand what is work done by a force. By force F acting on a body displaced through S, and that work done is defined by this simple relation. So for example, if we have a body that is making a displacement like this from this position to some position like this. So after some time this block is reaching here, and during that time one of the forces acting on the body is represented by this vector. So as the body is moving, this force is continuously acting on it. And this may not be the only force, there might be other forces acting on it. But we are talking about the work done by this force. So the work done will become Fs cos theta, okay, where force is in newtons, displacement in SI units is in meters. So work done becomes in joules. The unit of work done is joules. Okay. So this is the definition of work done by a force. Okay, so are you clear with the definition of work done? Now similarly we'll come back to the definition of power, but before that let us look at an example of the application of virtual work theorem. So next example of application of virtual work theorem. So in this particular example, let's say we have this type of a system consists of a block, string attached to a pulley, I mean string going round a pulley, then the string going around another pulley here. Finally, the string is attached to a fixed ceiling kind of thing. This is another block here. So this type of situation which you've seen before. So if this block has an acceleration of a1 and this block has an acceleration of a2, or at some instant this has a velocity v1, this has a velocity v2. You want to find the ratio a1 is to a2 or the ratio v1 is to v2. So we have learned this type of problem earlier. Okay, Krish, I will come back to that, but first let's understand this virtual work theorem here, how we'll apply it. So we have understood this earlier by thread length conservation. Right? All of you know that this ratio will be 2 is to 1. We know that this ratio will come out to be 2 is to 1 by thread length concept. But now let's apply virtual work theorem. Okay? So in virtual work theorem, what we'll understand is that the thread being massless, there's a uniform amount of tension acting everywhere like this over here. So we will apply the statement of virtual work theorem that for the system consisting of blocks A and B, okay, the pulleys plus the thread of this system, tension is an internal force. Okay. So therefore, net work done by tension should be equal to 0. So this will be the statement of the virtual work theorem. And now we'll apply that statement and we'll see how it gives us the constraint relation. Okay. Now from here, let us say after some time, this block has moved here. Okay. And this block has moved together with the pulley here after some time. So the displacement of block A is S1 and the displacement of block B is S2. So while this displacement is happening, what we can observe is that on block A, okay, tension is acting horizontally like this and the block A is making a displacement of S1 like this. Okay. So work done by tension on block A, say that W1 or whatever WA is equal to TS1 because they are parallel vectors. You can see the dot product will be like this. Okay. Now similarly, if you look at the situation of block B, now that is very interesting because on block B, remember the pulley is attached to block B. So you can think of the pulley as part of block B. So there's a double tension acting on block B. And block B is making a downward displacement like this. It's going from here to here of S2. So work done by tension in the thread on the block B, let's say WB, ये कितना हो जाएगा? It will be minus 2t into S2. Why minus? Because the vectors are in opposite direction. The net tension acting on B is 2T and is acting upwards, whereas the displacement is downwards. So this is at 180 degrees. Okay, so that F dot S is becoming 2T into S2 into cos 180. So it's becoming minus 2T. It's 2 like this. Okay. So that's done. Now the other thing is work done by tension anywhere else is zero. Because you can see that tension is also acting on this pulley here, but that pulley is not displacing. The pulley that is attached to this side, here the work done by tension is zero. Okay. Because the displacement is zero. Okay. Similarly, there's also tension acting at the ceiling at this point here. But again, the work done by tension here is zero. So in this system, tension is acting in a number of places. But out of that, tension is doing positive work on A and negative work on B, and it's not doing work anywhere else. Okay. So in here, see that as A and B move through displacements which are shown as S1 and S2, tension does positive work on A. We saw that WA was plus TS1 and negative work on B minus 2TS2 and no work at any other point in the system. Okay. Therefore, net work done by the tension is the work done by tension on A plus the work done by tension on B, and that should be zero. Net work done should be zero by tension. This is the virtual work theorem. Okay. So that tells you that plus TS1 minus 2TS2 should be zero. So S1 should be equal to 2S2. It's your first level of constraint relation. Differentiate this. So V1 is equal to 2V2. Second thing, and A1 is equal to magnitude of A1, that is 2 times A2. Is the third thing. Okay. So we are getting from here to here by differentiating. And then once you got here, from here to here again by differentiation. Okay. So this is a rather simple example, but you can see how the application of virtual work theorem is working out over here. So just make a note of this properly with all the explanations and everything. Make sure you read through them and understand. Okay. Then we'll get back to more examples and we'll see that this theorem is really powerful when the system is more complex and counting the thread length becomes very lengthy. So this becomes a very powerful method compared to that. Okay, since some of you have not written down the earlier part also, Krish in particular. This part, the work done part or the theorem before that? Krish, this is the part you have to note down or? Okay, okay. Yeah, work done Tej is zero in these cases because you can see the displacement is zero. Na? यहाँ पे tension is acting at this point on the ceiling, but that point is not moving. Na? So work done is F dot S, but the force is tension, but the displacement is zero at that point. Same for the pulley. These two tensions which are acting on the pulley, they're acting at points which are having zero displacement. Kunal, actually, the whole concept of virtual work theorem comes from Newton's second law. Every action has equal and opposite reaction. So any internal force within a system acts in such a way that both action and reaction are within the system. So they cancel each other. That is why the net work done is zero. So basically it's like an extension of Newton's second law. I mean Newton's third law. No, don't get into shortcut methods like ratio by looking at number of tensions, because that becomes very different when there are angles and all that involved. Okay. You might have seen in some guidebooks and all that you can count the number of tensions and calculate the ratio that way, but that is only in the case where the strings are all vertical or horizontal and vertical. The moment there are some angles involved, that becomes very different. That is why I've never taught you the method of counting the number of strings and ratio that way, because that is a very incorrect method. Equal and opposite, yes. That was by thread length. Earlier I told you na, by thread length. You can see I've taught you that method of thread length earlier. Na? So where there is only two pulleys and one string, thread length is the easier method na? Because you can directly see in this diagram. See, ये diagram में आप directly आप ऐसे समझ सकते हो ना, that if the block B is coming down by distance x, how much thread it is pulling? It's pulling 2x amount of thread. Na? So how much A will move? A will move by the amount of thread length this is pulled. So that's twice. So in this particular example, thread length method is easier. But eventually, when you practice, both the methods will be easy. Okay. So anyway, hope this method is clear to all of you. Okay. Now let us look at a more tricky situation. Okay, you have to write down the last part. Yeah, that's what I'm saying, Diti. It is usually correct because usually we have seen those type of problems where there is no oblique angle involved. So so far we have seen only the easy type of problems. But that method of counting the number of tensions and inversing that ratio, that is not correct when there are angles involved. Okay? So in general you should avoid that method. Okay? When you get used to virtual work and virtual power method, you will find this equally easy as counting the number of tensions. It's the same thing as counting number of tensions, but along with that you also keeping an eye on the angles involved. Okay, so that's why it's a safe method. You can't make a mistake with this. Okay, let's look at our next example, which is, let us say something like this. So this is also something that the type of problem we've seen earlier, but we will now apply the virtual work method to understand it. So this time, let's say we are solving everything in the question. Instead of just solving the ratio, we are given that mass of A is, let's say, 4 kilograms, whereas mass of B is 2 kilograms. We have to find their accelerations. So as you can see, free body diagram will give you two equations, but you will have three variables because they will have different magnitudes of accelerations. They will not have the same magnitude of acceleration. So you can see that if supposing I make the wrong assumption that this one is coming down and this one is going up. So you'll see that we'll actually get A1 and A2 with negative sign because 3t is acting on this and t is acting on this. The mass of this should have been 6 kg for balancing. So since the mass should be in ratio 3 is to 1 if there's equilibrium. So the ratio is less than that, and it's 2 is to 1. So actually A should be going up. But deliberately I'm taking the direction of acceleration to be wrong. And I'll show you that we'll just have to adjust with the negative sign. Rest it will take care of. But before that, you can see here that on block A, the net tension acting is 3T. Okay. And I'm assuming that it's going to make a downward displacement after some time of S1. Whereas on block B, the net tension acting is T. And I'm assuming that after some time it's going to make an upward displacement of S2. So my virtual work theorem that will tell you that net work done by tension within the system should be zero. So work done by tension on A plus work done by tension on B should be zero. So plus 3T, sorry, minus 3T S1 plus TS2 should be zero. So this is telling me that S2 is equal to 3 times S1. So by differentiating twice, I will get the relation that A2 is equal to 3 times A1. So this becomes my first equation. Even before applying Newton's laws, I, I should first understand the ratio of the accelerations by constraint relation. Now, like you've done within this one also, you will get by just ratio of tension se ho jayega. But the thing is that is an incorrect method. I'm just saying that is an incorrect method. It will work in problems like this because the strings are all straight, okay? But it is not based on 100% sound logic. It's just based on observation. Okay, now the other thing is you make the FBD of A. So I'm assuming it has a downward acceleration A1 and this has an upward acceleration of A2. So for A we have the free body diagram equation that weight minus 3T is mass into acceleration. That's my second equation. And for B I have T minus mg is equal to mass into acceleration. So third equation. And now we have to solve these. So just write this down up to here first and tell me what you're getting on solving equations 1, 2, and 3. What are you getting for A1 and what are you getting for A2? You should be getting both of them as negative quantities, which will show you that the direction has to be reversed, but the magnitude should be correct. You can take G as 10 only. So just see what you're getting first. I've got the acceleration so far. Okay. So let's solve the values. So we have this equation. Okay, then this one will become 40 minus 3t is 4a1. This one will become t minus 20 is equal to 2 into a2, which I will substitute as 3a1. So now what we'll do is we'll multiply this equation by 3 and add this. So 3t gets cancelled out. So we get 40 minus 60 is equal to 4 plus 6 into 3, 18, a1. So a1 we are getting as minus 20 by 22 or minus 10 by 11. And a2 we'll get as minus 30 by 11. So the minus sign shows us that the directions are opposite. So what this tells us that a1 as a vector will actually be upward acceleration of 10 by 11 meters per second square, and a2 as a vector will be downward acceleration of 30 by 11 meters per second square. So just check your solving equation solving. You should be getting this one. Okay. Here I'm just substituting MA as 4, G as 10, and MB as 3. So that's how we are getting this equation, and that's how we are getting this equation. Okay, and then we are substituting in this equation a2 is equal to 3a1. That's how this term is coming. Okay. So these are two examples of virtual work. Okay. Now we will also, before we see more examples, we will look at the case of virtual power. So it's just a slight modification. So in virtual power theorem, we say that the net power developed by an internal force like tension in a system is Z. Okay. So first of all, let's understand what is power. Okay. Power developed by a force F. It is defined as it equals to the rate of work done with respect to time. So power is nothing but this quantity. Okay. And yes. So basically it's a bit of application of calculus here. So what is happening is if the particle is making a small displacement ds, ds is the displacement in time dt, then the work done by the force during that displacement, then work done by that force F in time dt. So because it's a small time, it will be a small amount of work done. It will be F dot ds. Okay. So power will be rate of work done with respect to time. So it will become F dot ds by dt. Okay, but now since we know that ds by dt is nothing but the instantaneous velocity, so therefore power which is defined as rate of work done also becomes f dot v, because this can be written as f dot like this. Okay. So mathematically, this is the formula for power. The definition of power developed by a force is this, that it is rate of work done. So the formula for it becomes that power P is the dot product of force and instantaneous velocity. So power P is expressed in watts. Okay. So 1 watt is equal to 1 joule per second. Okay, because power is work done per unit time. Okay. Or that is the same thing as 1 Newton meter per second. Because yes. So just understand the definition and formula of power first, then we'll come back to the virtual power theorem. Okay, sure. But note this concept down first. Okay, so hope this concept is clear. Now just those who have missed out writing the previous example fully and just verify your equations and things. So just quickly take a look at the equation solving in the previous one, and minimize this. Yeah. So just finish off this quickly, then we'll come back to virtual power. Okay, good. So hope these examples are understood. Okay. So now let's come to application of virtual power. So now you would have seen a couple of examples like this in your module. Though these type of questions you will not find in HC Verma. Okay. So HC Verma deals with the more basic type of questions. So we have a situation like this now. So this example we are going to discuss, it's a pure uh, constraint relation example. We're not going to be solving any Newton's laws equations in this, but just the constraint relation. So this is a massless thread, or a light inextensible thread. Okay. Now both the ends of the thread, from this side and this side, are being simultaneously pulled down at the same speed v1, whereas at some instant this angle is theta, that is symmetrical to this angle theta. Okay. And the block is observed to be going up at a speed of v2. So if the two ends of the thread are being pulled down at common velocity of magnitude v1 equal to, let's say, something 1.8 centimeters per second. Okay. Find the upward velocity of the block at the instant when theta is equal to, let's say, 30 degrees. Okay. So as the block is going up, you can see that that angle will keep changing. At some instant, it's like this. After some time, the block reaches here, so the angle changes. So like that, the angle keeps changing as you're pulling the string down. So that's why I said at an instant when the angle is so much, because the angle is an instantaneous quantity. It is changing with time. That kind of thing. So this is an ideal example where you will see the benefit of using the virtual power theorem. So massless thread, so uniform tension in magnitude everywhere. And let us just name the ends of the threads as points P and Q over here. So here we'll use the virtual power theorem that the net power developed by tension within the system should be equal to zero. Okay. And what are we taking as system as? System is the block plus thread plus the pulleys. So for this now you can see that at the ends P and Q, the tension acting is vertically upwards, and the velocity of those 2 points is downwards. So same magnitude of tension is acting vertically upwards, and these 2 points are having a downward velocity of v1 each. Okay. Whereas if you look at the block, now the block's situation is very interesting. Block with the pulley as part of it and all that. So इसपे क्या हो रहा है, that amount of tension acting is the vector sum of these two tensions. Tension here and tension here. Whereas the velocity of the block is a vector whose magnitude we don't know just now, but its direction we know is vertically upwards because of the symmetry, because the angles are same on both the sides. So this is v2, and this angle is equal to this angle. Okay. So power developed by tension at the point P, it is minus TV1 because the opposite directions. Remember, power is force dot product with velocity. Okay. At the block, it is 2 times TV2 cos theta. So this tension is also delivering TV2 cos theta. This tension is also delivering TV2 cos theta. And at the point Q, it is again minus TV1. So net power should be zero. It implies power delivered at the point P plus power delivered at the point Q plus power delivered to the block, this should be 0. So minus 2t v1 plus 2t v2 cos theta should be 0. So we get the relation that v2 should be equal to v1 by cos theta, which in this case will become 1.8 centimeters per second divided by cos 30. It's 30 only now. Yeah, it's 30. 3.6 by root 3 centimeters per second, or we can write this as 1.2 root 3 centimeters per second upwards. That is the velocity of the block at that particular instant. Okay. So just go through the question once, make sure you understand the whole thing properly again, and then we'll come back to the solution. Yeah, Krish, for NEET physics, you can just buy one single reference book, Arihant Physics for NEET by DC Pandey. Arihant Publications, Physics for NEET by DC Pandey. That's actually a series of 5 books, but right now you can purchase Mechanics 1, which will have all these topics. There is Mechanics 1, Mechanics 2, Waves and Thermodynamics, then Electricity Magnetism 1, Electricity Magnetism 2, like that. There's a series of 5 books in all, 5 to 6, I think. But and of course HC1. As a student for NEET, you should at least do the solved examples from HC Verma. DC Pandey. Yes. For JE, there's a separate book, DC Pandey Physics for JE Mains and Advanced. And for NEET, there's a separate book, DC Pandey Physics for NEET. So medical students, I mean medical aspirants, you should look at the Physics for NEET book. And engineering aspirants, you should look at Physics for JE Mains and Advanced. From the same publication, Arihant publication by the same author, DC Pandey. Okay, so hope you understood the question. Now come back to the solution. So this is where you'll see really the virtual power method gives you a very quick solution for this. I'll show you the thread length conservation method also, but that's going to be very lengthy. So hope this method is clear to all of you. Okay, now let's understand that if I didn't have virtual power method, how we would solve this. So we'd have to use absolute basics. We'd have to use calculus and thread length conservation. So alternate method of this, thread length conservation. So for that thread length conservation method, let me pick up this diagram to save time. This diagram has too many things labeled, so it doesn't matter. Okay, so now let's do one thing here. Let us take this thread length to be x, and because it's symmetrical on this other side, this is also equal to x. Okay. And let us take this thread length to be some z, though it's not really along the z axis or anything. I'm just saying it is z. So I have 2x plus 2z is the total length of the thread, which is constant. Total thread length. So that should be constant. Okay, that's the first thing. So that means x plus l, sorry, x plus z is a constant. So that means rate of change of x plus z should be zero, because rate of change of a constant is zero. So in other words, dx by dt plus dz by dt should be zero. Okay. Now in this diagram, see this point is going down at v1. This point is going down at v2. Sorry, v1. So I know that dx by dt is positive of v1 because x is increasing at the rate of v1. Okay. But I don't know anything else in particular because this v2 is not along this line, it's in a different direction. So what we'll have to do is we'll have to incorporate one more variable. So what we'll do is we will take this length as d because it's a fixed length, whereas let's take this length from here to here as y. So we can see that z is equal to square root of y square plus d square. Okay, where d is a fixed length, it's not changing with time, but y is decreasing. So in fact, we know that dy by dt is nothing but minus of v2 because v2 is the rate at which that point is going up. So it's decreasing the value of y at this. Okay. So we are going to use this and this along with this primary equation along with this. Okay. So how we are going to use this is, of course, this angle is theta, remember. So dx by dt plus, now z we will write as square root of y square plus d square. This should be 0. And next step we will apply the chain rule concept. So dx by dt plus, so become 1 by 2 into y square plus d square to the power minus half into 2y into dy by dt. This should be 0. So we have dx by dt plus y upon root of y square plus d square into dy by dt is equal to 0. Okay. Now we are going to use these little equations, this one and this one. And we're also going to use the geometry from above of the triangle. So further in this you'll notice that y upon root of y square plus d square is nothing but y by z, which is nothing but base upon hypotenuse for that angle. So it is cos theta. And so this becomes plus v1 plus cos theta into minus v2 is equal to 0. So this is from equation 1 and 2. You are substituting these things. So you are getting that only, that v2 is equal to v1 by cos theta, which is the same as the relation we had got by the virtual power method. But you can see the number of steps in virtual power method was much less. You just had to see the cos theta thing properly. Okay. Whereas here there is, you have to set up the thread length in terms of variables, then differentiate. Then when you are differentiating, there's the added complication of the chain rule application. It's very avoidable, this method, and it's very advantageous to use the virtual power method in a question like this. Okay. So this is a seriously advanced type of application of constraint relations, the type you would expect more in JEE Advanced, not for NEET or not for JEE Mains. Yes, just note down the key things in this method also, so that you know that there is another way of solving also, even though it's more complicated. And also it gives you the confidence that what we have got from virtual power method is correct, no? Because ultimately it's agreeing with a more fundamental principle, which is that the thread length should remain conserved. There is also an application of calculus. This could also be a calculus based question, how you can develop the constraint relation by using differentiation and calculus. So make sure you understand the differentiation by chain rule method over here. See, this is differentiation of square root of y square plus d square. So it is basically differentiation of square root of a function. So that becomes 1 by 2 times that function to the power half minus 1 into then rate of change of that function. Okay. So that's how that becomes 1 upon 2 root f into that differentiation of that function. Now what is that function? Y square plus d square. So further it becomes 1 by 2 times, differentiation of y square plus d square will become 2y into dy by dt, because remember you're not differentiating with respect to y, you're differentiating with respect to time. So that's how we ultimately get this. Okay. So this in itself is a complicated calculus problem for you at this stage. How you differentiate something like this, square root of y square plus d square with respect to t, where d is a constant but y is something which is changing with respect to time. So how we got from this step here to this step, this step to this step, this one, this kind of thing. So make sure you note this down and you're clear with this. नहीं वही है ना, देखो क्रिश, you're not differentiating with respect to y, you're differentiating with respect to t. That's why that last term dy by dt will also come. See what is 2y. So there is one more like half step involved in this. Just a minute. That last half step involved in this is, see, when you're doing this step here, na, d by dt of y square plus d square. There's one more application of chain rule in this. So this is equal to d by dy of y square plus d square into dy by dt. And this is 2y into dy by dt. So this thing has to be substituted in place of this. So that's how we're getting this. Okay, so it's a little bit complicated, but again, from your calculus point of view, you have to know this. Okay. In this question, we might never use this method because we already know the virtual power method. But as a student of calculus, the basics, you should know this. So that's that. Okay. Now let's come back to Newton's laws type of questions. So next example is again something where I will show you that in a system of pulleys type of problem, how much advantage you can get out of by using the virtual power method. Okay, so we have this time a situation like this where so it's like this string is attached to the axle of this pulley, and then we have one more string which is attached to the axle of yet another pulley. So these are the again tricky type of questions, and so we have a system of three pulleys and also multiple threads. So that is what makes this type of question a little bit more tricky while solving. So this pulley here is attached to the ceiling, but this pulley is not fixed to anything. It is just hanging like this. So we have a system of three pulleys, and also three different threads. Just, just the diagram further. Right. So we have this situation. finally one more block attached to it. So this is the block A, this is the block B. So given mass of E is, let us say, 5 kilograms, mass of B is 10 kilograms, G is 10 meters per second square. Pulleys P1, P2 and P3 are massless and smooth pulleys as usual. Okay. And all threads are massless and inextensible. Okay. So first of all, we want to find the ratio of the magnitude of accelerations of A is to B, and then we want to find these values in meters per second square. Okay, so just take down the question first. We'll discuss more about it. Okay, so hope you've taken down the diagram. Now, one very important thing to understand here is that there are three different strings. So if this string has a tension T1, that T1 has the same magnitude everywhere, like this. Okay, but the second string will not have the same tension. It will have a different value of tension. So let's say that is T2. That will be like this. Okay. And similarly, now the third string, that will also have a different value of tension everywhere. There's three separate strings, so they have three separate values of tension. So the first and foremost thing we have to understand is that any massless body, or you can say for any massless body, mass tending to zero, the net force on it, which is mass into acceleration, tends to zero. So this concept that I'm talking about, that a massless body, the net force on it is zero. This will apply to pulleys P2 and P3. So first of all, we'll apply this concept to these two pulleys, P2 and P3, okay, because they are massless pulleys, and there are multiple tensions acting on it. So if you look at these two pulleys, you'll understand what I'm saying, why it's important here, because that will give you a relationship between the tensions. So if you see the pulley P3, okay, that had tension T1 acting downwards like this and like this. You can see that on this pulley P3, you had two T1s acting downwards, and you had T2 acting upwards, and it's massless. So net force on it should be zero. So that is telling you that T2 is equal to 2T1. So this becomes in fact our first equation. And similarly, if you see this other pulley T2, अभी इसमें क्या हो रहा है? There are two tensions T2 acting downwards, and the tension in the third string in my system T3 acting upwards. So this is also massless. Okay, so T3 should be equal to 2T. So you can see that T2 is equal to 2T1 and T3 is equal to 4T1. Okay. So suppose we say T1 is equal to T, T2 should be written as 2T, and T3 should be written as 4T. Just like this. So even before we start with the virtual power or virtual work method or whatever, we should make use of this. P1 is also massless, but P1 से उतना मतलब नहीं, because P1 has some kind of reaction force acting at the axle, and that is just balanced by T3 and T3. So if this reaction force is R will be equal to 2 times T3. But main thing is we are concerned in the relationship between the tension T1, T2 and T3. So that is why for us these two pulleys are more important in the analysis. Okay. Now once we are done with this, now we will understand the application of virtual power theorem. So if we assume, for example, that this block A is going up with some instantaneous velocity v1 and acceleration a1, and at that same instant of time this block has a downward instantaneous velocity v2, downward acceleration a2. So now we will incorporate virtual power theorem. If you look at that block A, on that there was a total tension of T3, which was 4T, plus T2, which was 2T, plus T1, which was T. And we assume that it had an upward velocity of v1. So power delivered by tension on A, that is plus 7T v1. Basically it is T3 plus T2 plus T1, that is 7T. Now if you look at the two pulleys P2 and P3, you need not worry because the net force is only zero. So it doesn't matter what the velocity is. It might be coming down, might be going up, whatever be the case. But the power by tension is zero on this. Same for this. This might be coming down with some velocity, but the net force only is 0, 2t upwards and t downwards. So the net force due to tension is 0, so power is 0. Okay. Which brings us to block B. Now block B had a single tension T1 equal to T acting upwards, and it has a downward velocity of V2. So power on the block B by the tension is minus TV2. So when we put together the net power delivered by tension, that should be 0. So power on E by tension plus power on B by tension should be 0. So plus 70 V1 minus TV2 should be 0. So interestingly here, the constraint relation is like this. V2 is equal to 7 V1. So E2 is equal to 7 E1. This is the answer to the first part. Okay, so make a note of this first, then we'll come to the second part. So once you get used to this, it's very easy. You will just be able to see that the tension acting on this one is 70 and on this one is only T. So when you apply the virtual power, you can see that plus 70 V1 minus T V2 should be 0. So in one step, you will be able to write this equation. This equation that we got now, you'll be able to write it in one step. Just looking at this diagram. And then the rest is for the second part, just free body diagram. So for E, the net tension is 70 upwards. The weight was 50 newtons and it's having some upward acceleration E1. So we have 70 minus 50 is equal to 5A1. Directly writing with the mass. Because mass of E was 5 kg. For the block B, we had just T acting upwards, weight equal to 100 newtons acting downwards. Okay. And we had mass of B was 10 kg. So we have 100 minus T is equal to 10A2. Second equation, or rather this is the third equation. This was the second equation because this was already there. Now we will incorporate this over here. So this will become 100 minus T is equal to 70 A1. So T2 equal to 70 A1. And this equation is 70 minus 50 is equal to 5 A1. Now solve these two. So to solve, you can just multiply this by 7 and add it to this. So 70 cancels out. So we get 700 minus 50 is equal to 490 plus 5 into A1. So from that, okay, whatever that is, you can round it off later. And A2 will just be 7 times A. So this is like a, one of the more tricky type of applications of constraint relation. But you can see that virtual power makes this very easy. Okay. Now, if you try to use thread length conservation, this is going to be quite tricky because you will have to conserve three different thread lengths, L1, L2, and L3, because there are three different threads. So you'll end up making a very messy equation and a lot of trouble in finding out the relationship between the accelerations. But this is super easy once you understand the virtual power. So this is very important. Okay, what we have discussed in today's lecture. Yes, Tej, what is the doubt, beta? ऑब्लिक एंगल लिए था ना बेटा, वो वाला क्वेश्चन में जैसे था, that tension was acting like this, no, through the pulley. So there was some angle involved. So this is an example of tension acting obliquely, not acting along a straight line. That was the meaning of when there's an oblique angle involved. Understood? Okay. Okay, people. So very important lecture today. Make sure you go through the examples we've done in class. Okay, and try to target finishing H.C. Verma's Newton's laws of motion at least by this weekend. Okay. And start with the module questions also from exercise 1 and 2. The ones which don't have friction, only Newton's laws of motion. Those questions, try them out. Okay. So we're done now with the all the methods and tricks and all that of solving problems. But one or two more sessions we will do of discussion of questions of Newton's laws before we move on to friction, which will be the next chapter. Yes, so you have to do that. Huh? You have to find the relation between T1, T2, and T3. T. That's correct. Okay, people. Wish you all the best. That's it for today's lecture then.